Doing this video is a continuation of my last one in which we introduced the concept of a combination, which is really counting the number of groupings that exist when order does not matter. Okay, and so in this video we're going to focus on combinations, but in conjunction with what we call our fundamental counting principle, or at least the multiplication rule. Okay, so I'm just going to run through a few examples here of how this is slightly different than running simple combinations, but we're going to do them, I guess you should call it a compound combination. Okay, so it says a restaurant serves omelets that can be ordered with any of the ingredients that you see here. So vegetarian options, we have green pepper, red pepper, onion, mushroom, tomato, cheese. I don't know, this one's probably arguable, huh? And then we say meat, we have ham, bacon, sausage, steak. So suppose we want exactly 2 vegetarian ingredients and exactly 1 meat ingredient in the omelet. The question really here is how many different types of omelets would it be possible to order? Okay, so what we want to consider is this. When it comes to how many omelets that are possible to order, what we're going to have to do is this. We're going to have to choose a vegetarian option. We're going to have to choose a meat option. But the idea is we're not choosing exactly one thing from each list. So I can't just say that it's, 6 options times 4 options is 24 different outcomes. What we have to say really is this. We have to choose 2 from this list of total of 6 right here. So what we're saying is, if I want to know how many ways I could choose 2 options from 6 total options, then what we're really saying here is that our n is 6 and we're making groups of 2, and order doesn't matter in which I put them in my omelet. So we would say that I've got 6 total items here and I want to choose 2 at a time. So what this is really represents how many ways you could get 2 items from the total of 6. Now when we talk about meat, we say, total here, we would say it's a little bit different. We say we have 4 total options and we're choosing groups of 1. Okay, so we say 4 objects. I want to choose 1 at a time. This is how many ways I could get 1 thing from 4 things. So now, evaluating this, recall that our formula for combinations is n choose r, where we have n factorial over r factorial times n minus r factorial. And so what this yields is a situation where we would say, then I'd get 6 factorial over 2 factorial times 6 minus 2 factorial. So this is the number of ways we could get 2 vegetarian ingredients from 6 right there. We'll have to evaluate that. And then also this we say the meat ingredients would be 4 factorial over 1 factorial 4 minus 3 factorial. Okay, and simplifying this, what we end up with is really this. We say 6 factorial. I'm going to write on top of this here 2 factorial. That's not going to work. Sorry about this. We could say that if I were to simplify this, why don't we switch colors here and I'll bring it down over here. We'd say that I get 6 factorial over 2 factorial, 4 factorial, all of that times 4 factorial, 1 factorial, which is just 1, times 3 factorial. And so we can definitely go through and simplify these out, but because I have a calculator and this is going to be such a big number, let's go ahead and multiply these straight across. And what we get is this. We get clear, memory clear. We get 6 factorial, which is 720, times 4 factorial on top. And I'm going to get a response here, or a value. So at the top comes out to be 17280. We say 17280. I wouldn't normally write this down, but that's not very big, so I'm going to go ahead and leave it on the screen there. And then if we took the bottom here, clear. So we have 2 factorial times 4 factorial for the denominator in our first ratio expression here, rational expression. And we say over here times 1 factorial times 3 factorial. I'm going to neglect the 1 factorial because it's just 1. And we'll take that times 3 factorial, so we get 288. So the total number of possible combinations for an omelet here in this instance would be our 17280. And we will divide this by 288. And so we get 60. Okay, so we say 60 possible omelets that can be made here. The idea, though, that I want to point out in this video is that we used combinations, but we used it with the fundamental counting principle. So let's go find out how many ways exist to do each individual thing, and then multiply all those together. And again, we say, suppose in another visit we wanted exactly 3 vegetarian ingredients and exactly 2 meat ingredients. How would this be different? How would we order differently here? And so we'd say, we still have vegetarian, we still have meat, but in this case, we would say that, of the 6 vegetarian ingredients, we're choosing exactly 3. So how many ways could we get 3 things from 6 things if order doesn't matter? Well, it's 6 choosing 3. And again, here we would say that in this case, I have 4 different meat ingredients, but we want groups of 3. So we say, how many ways could I do this? And so again, we could multiply this out, but we say 6 factorial, and this is going to be over 3 factorial, 3 factorial. And then this is going to be here 4 factorial over r factorial 4 minus r factorial. So 4 minus 3 factorial is 1 factorial. And again, we'll get some expressions here. Let me go ahead and quarantine this off here. But our first thing we should do is go ahead and evaluate our numerators. So we'd say, okay, in this case we get 6 factorial times 4 factorial. And I think we still get this 17280 here. So we get 17280 upstairs. But downstairs we have 3 factorial. So we say, all right, here we go. We say 3 factorial times 3 factorial times 3 factorial times 1. And we get 216. So this time, there are going to be slightly fewer combinations, but because we are choosing more at a time each time, so there's less ways to do it. So we have 17280 divided by 216. So we get 80. Actually, more combinations, my bad. 80 possible outcomes here. Because we are choosing more each time, there's more ways to do it. But yeah, so when you look at this over here, example number 3, we're saying, okay, well, how would I do these? Well, really, we can show our work, and I want to show my work on this first one here. Again, 10 choose 3 would be 10 factorial over 3 factorial, 10 minus 3 factorial. In simplifying this, we get 10 factorial over 3 factorial, 7 factorial. And so on a normal day when I show my work, what I would do is I would tend to split the top up. We say 10 times 9 times 8 times 7 factorial all over 3 factorial, 7 factorial, where you can see that we can slice the 7 factorial out. And so we really get 10 times 9 times 8, and this is all going to be over 3 times 2 times 1, where I suppose the 3 would go into 9 3 times, and 2 might go into 10 5 times. And so we end up with 5 times 3 times 8, which is 15 times 8. And that would be 120 possible combinations here. And we could have found this out on a calculator. What we would do for something like this is actually evaluate on the calculator. So we can show all work in reasoning, but we say 4 factorial over 3 factorial, 1 factorial. And we would say, okay, so 8 factorial. And this would be over 2 factorial. 8 minus 2 factorial, 6 factorial. And again, let's see what kind of values we're pulling out here. But multiplying these out, we would say on top we get 4 factorial times 8 factorial. And then I'm gonna store that to the memory here, memory plus, and then we're gonna divide that in parentheses by 3 factorial times 2 factorial times 6 factorial end parenthesis, and when we divide this out we get 112 possible outcomes. Okay. So that is how we would evaluate combinations using the fundamental counting principle, but also multiplying combinations together. And again, most calculators are going to have buttons where you can just say 4 choose 3 times 8 choose 2, and it's a lot quicker. Cheers.